Okay. It's my great pleasure and honor to be speaking here in this YHSA forum. So my thanks to the organizers for this event. I will be talking about the topic of from complex numbers to rational points. Okay, I want to start with something back in high school days. So on the left, you see this book, which is Introduction to Transcendental Numbers. I got interested in complex numbers early in high school, and this is a book I found in the City Hall, the public library in Hong Kong. And there one sees the importance of these complex numbers, the square root of -1 to start with, which can be used in a very effective way to study transcendental numbers. What are algebraic numbers? They satisfy algebraic equations with integer coefficients. Like square root 2 is an algebraic number because it satisfies x squared minus 2 equal to 0. Pi does not satisfy such an equation, but this is a big theorem at the end of the 19th century. On the right, you see this book, which is the Annals of Mathematics. Here is an issue in which I publish a joint article with my collaborators, Jonathan Pila and Jacob Zimmermann, which is called the Chanuel conjecture, a theorem on Shimura varieties. And I want to say how they are related. Okay, to start with, let me do it historically. So Gauss is a geometer, a great geometer, and number theorist at the same time. He said that mathematics is the queen of sciences and number theory is the queen of mathematics. I take this as a guiding principle, and I more or less believe in it. So he did geometry, intrinsic geometry, well, to start with extrinsic geometry by studying surfaces in R3. But there's something intrinsic to it. If you look at a plane and also a cylinder, they don't look alike, but actually, if you look at the metric, they are isomorphic to each other. And so there is something called curvature, which is intrinsic. And this was captured by a Greek theorem of his called the remarkable theorem. So Riemann, his student, then introduced a notion of geometry which is intrinsic. It's called Riemannian geometry, starting just with what we call now the Riemannian metric, namely bilinear. It allows you to measure lengths and angles between the vectors. Now then comes the square root of -1. So x squared plus 1 equal to 0 has no solution. But if you assume that there is such a solution, you just extend the number system, you get complex numbers. And on the right, you see this Argand diagram, this polar coordinates. What's important about complex numbers? Well, of course, one indication is that there is a fundamental theorem of algebra, or to any polynomial equations of degree bigger than 0, in which you have complex coefficients, you will always be able to find a solution. And actually, you find exactly n solution accounting multiplicities. So a disk in a complex plane is a one-dimensional complex manifold. So pasting this together, such that changes are holomorphic, will lead to so-called one-dimensional complex manifolds. It's called a Riemann surface. So you see the name of Riemann everywhere. When you extend calculus from the real domain to the complex domain, you get what are called complex differentiable functions, which can be also called holomorphic functions. They're conformal in the sense that they preserve angles. So for instance, the sphere can be given such a structure. You do stereographic projection, and that's how they draw maps. But they drew maps in the old days. Angles are preserved, although lengths are sometimes magnified or shrunk. Now, then if you are on a complex manifold, you can introduce Riemannian metrics also, but there are certain metrics which are better adapted to the complex structure, and those are called Kähler metrics. So for instance, the projective space, which is a compactification of the complex n-dimensional Euclidean space, is Kähler. Now, I got to know the complex numbers when I was learning calculus in Form 2, and I was really amazed by the fact that one can do certain integrals very elegantly using Eulers formula. And here is the Eulers identity. It says e to the power I pi plus 1 is equal to 0. Also, e to the power 2 pi I would be equal to 1. Now, in the geometric side, you have a classification, a complete classification of compact Riemann surfaces according to genus. Now, on the sphere, there's only one possible complex structure. But already on the donut, you would see different kinds of complex structure depending on your choice. Then there's a notion of a complex curve, which is the same as a Riemann surface, of a rational curve, which is a Riemann sphere, and elliptic curve, a genus 1 curve. And then you have higher genus curves. You have projective space, you have submanifolds of it, and also quasi-projective manifolds, which is obtained by removing a thin projective subvariety from a projective variety. Then comes the great geometer and mathematician and great mathematician Henri Poincaré, who together with Kerber proved the uniformisation theorem. That is the classification of all Riemann surfaces according to their universal covering. This is according to the curvature. You have positive curvature in the case of sphere, flat curvature in the case of the Euclidean plane, and then the disk with negative curvature. Now, I did a lot of work in the case of the Riemann sphere, but today let me talk about the genus 1 situation. If you are on the complex plane and you introduce a lattice, you can mod out by the lattice to get a donut. And the lattice can be generated by 1 and tau in this diagram. And then depends on where tau is located, the quotient that is obtained by folding the two sides of fundamental parallelogram together, and then once again, would change. However, tau and tau plus 1, for instance, would give you the identical or isomorphic elliptic curves. So how do we classify them? Well, actually, we can classify in the following way. You take a lattice generated by 1 and tau, and then a tau and tau prime would give you isomorphic elliptic curves if and only if they are obtained by 1 substitution. And the substitution is given by a matrix A, B, C, D, which is in SL2Z, namely that the determinant is equal to 1 and the coefficients are all integers. Okay. Now, there's a famous J function. You may think about the J function as an analog of the exponential function. It tells you that tau and tau prime would be isomorphic if and only if their J values are the same. This J function can be computed using the lattice generated by 1 and tau, and it leads to an isomorphism, which is the following: that the J function establishes an isomorphism between the set of isomorphism classes of elliptic curves with the complex plane. Now, this is a famous picture. The gray area, which extends all the way to infinity, is a fundamental domain for this quotient, H mod SL2Z. Now, the upper half plane is actually isomorphic to the unit disk. In high dimension, you have something analogous. You can take the uniball. These spaces are so-called symmetric, biosymmetric domains. They are homogeneous, certainly, but more than that. And there's a classification of by Élie Garton of this biosymmetric domains consisting of classification, first of all, of Lie groups, semi-simple Lie groups, or simple ones, actually. The classical domains consist of 4 series, and there are 2 exceptional cases pertaining to 2 exceptional Lie groups. Now, the quotients of these domains by certain lattices are then important objects classifying certain notions, certain concepts in algebraic geometry or number theory, like in the case of elliptic curves. And then you can have higher dimensional analogs, which is the classification of well, high dimensional quotients like Cn mod L, which are projective algebraic. These are called abelian varieties. Now, then comes the topic of transcendental numbers, which I referred to right at the very beginning. This is a formulation by Search-Lang of line of argument of Gauss von Schneider. It says the following. Well, this way, one will be able to prove that pi is a transcendental number in the following way. You look, for instance, at the exponential function. Okay, so take the exponential function, and you want to look at e to the power pi, e to the power pi I. Okay, okay. So the statement is the following: if you take alpha to be a non-algebraic number, or you take alpha to be an algebraic number which is non-zero, then the statement is that e to the power alpha is not algebraic. The proof goes as follows. Suppose that e to the power alpha is algebraic. Then you take the number field generated by alpha and e to the power alpha. So this is a number field. You can think about this as just rational numbers. You can already get something as an example. And then you look at multiples. So take alpha, 2 alpha, 3 alpha, and so on. You will have an infinite number of such numbers such that the exponential function and the function z, the coordinate function, both take algebraic values. Now, then the main theorem, according to Search-Lang formulation, says the following. If you look at a field of functions, like the exponential function and the coordinate function z here, and if they are of a finite order, meaning like exponential function, and if by differentiation you still get some function in this function field, then the set of points where both functions, both generators take values in K is finite, and actually it can be bounded. Now, in the case of the exponential function, you get an infinite number of such functions, such numbers, and there's a contradiction. The contradiction says that e to the power alpha is not algebraic, and from this one can conclude the pi and e are both transcendental numbers. Gauss von Schneider is something along this line. This alpha to the power beta is not algebraic if both alpha, beta, and algebraic, and alpha is different from 0 and 1. So Lindemann, in the year 1882, proved the following remarkable theorem. It says that if you take algebraic numbers which are Q-linearly independent, there's no linear relation among them using with rational coefficients, then e to the power alpha 1 up to e to the power alpha n are actually algebraically independent. Chanuel, who was a student of Search-Lang, formulated something according to which the transcendence degree of 2n numbers, so alpha 1 up to alpha n, are Q-linear independent complex numbers. The transcendence degree would be bigger than or equal to n. This is a big conjecture, and so far very little has been done beyond Lindemann's theorem. But something could be done by Alan Baker. This is assuming that e to the power alpha 1 to e to the power alpha n are actually algebraic, related. Then you're looking at the log function. What you could prove is that 1 log x1 up to log xn are linearly independent over q bar. So this was already a very big achievement, and Alan Baker was fused malus slightly before that. The example of the zero upper half plane. This is you take imaginary part of tau being positive, but instead of a number, you take tau to be a matrix. And the matrix is a symmetric matrix, and you have the Riemann bilinear relation. So tau is symmetric, and the imaginary part of tau is positive. This is an infinite domain, but it can be proven that it is isomorphic to a bounded one. So one of the classical series according to the list of Eddie Garton. Now, then there is something called the symplectic group, which acts on the upper half plane, like SL2Z acting on the upper half plane. And if you take the quotient, you also classify some objects. This is the set of isomorphism classes of abelian varieties, which are so-called principally polarized, which is a technical term. So you get something called a Ziegler-modular variety, and you have some analog of the J function. And then there is something called the Andreault conjecture. The conjecture says the following. You look at the elliptic curves, so the J function. If you take a point tau in the upper half plane and ask when tau and J tau are both algebraic numbers, this is very, very rare. And this occurs, according to Schneider, the author of Gelfand Schneider, would imply that the tau is a quadratic number. The Andreault conjecture concerns about infinite set of special points. These are called special points. If I give you an infinite set, a countably infinite set of special points on a Shimura variety simply means omega mod gamma. So this is a generalization of the complex plane, so to speak. In one dimension, this is just a complex plane, but you take some quotient, omega mod gamma. Normally, these are so-called hyperbolic if you take gamma to be torsion-free. And the conjecture is that if you take just infinite set and take the smallest algebraic set containing them, then this set is also omega prime mod gamma prime. And then came a formulation of the problem due to Zanier, which brought me to be interested in this problem. Well, Zanier, the number theorist in Pisa, formulated a strategy for solving the special point, the conjecture on special points. Namely, he was able to reduce this problem to two halves. One half concerning algebraic number theory, and the other half concerning complex differential geometry, or complex geometry, like more generally. So in this direction, I was working with some specialists in logic, in mathematical logic and number theory. The story goes as follows. So in the year 2012, Professor Wisholt of ETH, the university where Einstein graduated, was visiting Hong Kong U. And he brought me to the attention of the Andreault conjecture, this conjecture on the special points on Shimura varieties. I was really interested, and I told him what I could do from the point of view of complex differential geometry. The next year in 2013, he invited me to a conference at ETH, and this was a conference on arithmetic and geometry. And I was able to explain to the audience, primarily consisting of number theorists, an approach to the X-type problems, which are called functional transcendence problems, using a combination of complex differential geometry and algebraic geometry, namely some study of moduli schemes. So then there were lots of communication between me and the number theorist community, and this eventually brought to a collaboration in the form of an article a collaboration between myself and Jonathan Piller and Jacob Zimmermann. Jacob was visiting Hong Kong U, visiting the Institute of Mathematical Research at Hong Kong U in the year 2016, and we had lots of discussions leading to then on the basis of what he already did with Jonathan Piller, a final solution of the problem. Now, if I look at how the theorem is stated this way, this is an analogy. So in mathematics, there is a lot of mileage you can go with analogy, with analog. Certain results in one subject may be translated to another. In this case, actually, there's a proximity between the two problems. This is a problem about the transcendence degree of a field of functions. In the case of the Chanuel conjecture, it was a conjecture on the transcendence degree of a field of numbers. So the analogy goes a little farther than this. And although, of course, the statement is slightly different, there's an additional term of the dimension of a variety, but this is understood because we are restricting the functions to a variety, and the variety itself, the function field on the variety itself has a certain transcendence degree, which is given dimension V. Okay, so if I look at this, the analogy looks just like formal. There are situations where you have formal analogy, but the methods cannot be carried over. The methods actually did not carry over altogether, but it's certainly the case already in the formulation of problems that one is doing complex analysis. What brought me to the attention was Zanet's strategy and also formulation of unlikeness intersection, which goes this way. So it's the same problem, but formulated differently. It's formulated in terms of unlikely intersection. So I should say here that the analogy also has a certain, well, it's not complete. It says here that you have this inequality on the transcendence degree of these field of functions, Zi being functions on the covering domain, and the phi j being modular functions on the closure or on the quotient. So this is like putting in Z and exponential Z, something like this, in a slightly different context, namely on omega mod gamma instead of on the on C star. So then the analogy has to be, so to speak, modified in that you don't always have this inequality. You may have this inequality, you can have this inequality only if you rule out certain cases. So for instance, instead of getting this subset V in omega, we get V in some omega prime, which is smaller. Then the expected inequality would be, instead of N, you would have the dimension of omega prime, which could be very small in comparison to N. So the Chanel conjecture for Shimura variety says that you have this inequality provided that V is not contained in any weakly special variety. This in differential geometric terms simply means totally geodesic subsets, not just on omega, but the quotient also the totally geodesic subsets. So then this reformulation in terms of unlikely intersection says the following. You look at the graph of the analog, the J function, the uniformization map. And then the graph, since J is supposed to be highly transcendental, this uniformization map is highly transcendental. D is a very, it's an analytic set which is very far away from being algebraic. You take some algebraic W, which is in the product of omega and the quotient x gamma. And you assume that the intersection of W, the algebraic W, with D, which is the graph of this analytic transcendental map. And if the intersection has excessive dimension, has unlikely dimension, is bigger than what is normally expected, then the conjecture would say that the projection of one irreducible branch, U of to x gamma, would be contained in the totally geodesic subset Y, which is not entire is a proper subset of x gamma. Now, just this reformulation of the problem makes the problem completely different to me, because it says very clearly that this is a question in complex geometry about excessive intersection, and you can make use of moduli schemes of the set of all those W for which this inequality is satisfied, and look at the locus where this inequality is this inequality holds, so to speak, the bigger than instead of being equal to. And then together with works that were done already by many people, including my collaborators, using the mathematical logic and what is so-called model theory in mathematical logic, and the technology in complex geometry, also called tame complex geometry, with this complex differential geometric perspective and also algebraic geometric perspective, solution was finally obtained. Now, so how is this important to number theory? So although this is, so to speak, transcendental theory in function field, actually a conjecture that was also in its primitive form about the exponential function was a conjecture by Chanduel himself. How this would eventually lead to results actually in number theory concerning numbers. This has to do with the higher genus situation. If you take genus bigger than or equal to 2, there's a way by integration of forms to get this higher genus curve into something called the Jacobian of the curve, which is an abelian variety. So represented by a point in the zygomodular variety. So then again, this is a Shimura variety. Now, after embedding it, so normally this is an embedding. There are some exceptions. And then you can ask about the questions on rational points of embedded curve. And here is the result that were obtained by other people. This is the uniform model length conjecture by work of Dimitrov, Gauss, and Habecker. They were able to prove that not only you have finiteness of number of solutions, these are the Diophantine equations. They went back to Faltings in 1983 to prove the model conjecture, and now the model theorem, and namely that if the equations defining C are over a number field, then there are only a finite number of k rational points, which has entries in the field K. And this was a breakthrough at that point, and Faltings was fused malus in 1986. Of course, there are finite number, and now the question is, can you give some estimate on this number of solutions? So Dimitrov, Gauss, Habecker was able to prove a uniform model length conjecture, and namely that this can be bounded uniformly by the genus G, and a certain invariant on the Jacobian of the curve. This is the Mordell-Weil rank of the Jacobian, namely the rank of the abelian group of rational points on JC. And this was done by means of the generalizations of my theorem with Piller and Zimmermann, especially Gauss' generalization to mixed Shimura varieties. Gauss is now a professor in Germany. So there are many applications of this, especially to the Betti map for abelian schemes. And this application by Gauss and others actually was used in reaching a proof for the uniform model length conjecture, together with the Chanduel theorem on mixed Shimura variety, spanning from MOK, Piller, Zimmermann, and work of others, including those of Gauss. So this is how a dream of trying to do something in transcendental number theory finally brought me to work on a problem which has implications in number theory on rational points. So here comes the end of my lecture. Thank you for your attention.